Hello there, Algebra 2A students. The objective for this video here is to introduce to you our last transformation after translations and reflections, dilations. And I'm just going to take you through this first example, stop it, and then show you, maybe generalize a little bit, and then give you an option to kind of go through the rest of the page. I would first, if you haven't yet, try working through it. And then I'll put some of the mathematical words to it on what the effects that you've found are going to be. So pause right now, try it out, and then come back. We're going to graph the square root function in 4 different ways. And then these 4 different ways are going to come out a little bit differently, and we're going to describe each as it's going to be a stretch, compression, a horizontal stretch, or horizontal compression. So, oh, cat's out of the bag. All these numbers in front or inside the function, when they're being multiplied, will induce a dilation of some sort, either a stretch or a compression in the horizontal or the vertical fashion. So let's pretend like we aren't quite sure what this is going to be. Let's graph the original square root function. To set you up first, let's make the grid so that it is going to be in the first quadrant only. That's where all the action's going to happen. So set up your grid so that we're just seeing quadrant 1. And you don't have to label every single point. I'd probably do every 5. 1, 2, 3, 4, 5, 10, 7, 8, 9, 10. On the x-axis, and 5, 10, 15, 20 on the y-axis. And 20. And once you've got that, we're going to take it from the first column. It's always good to start with that parent function, the square root of x. And these points here are the ones that we should be pretty used to. 0, 0, 1, 1, 4, 2, and 9, 3. I'll graph that original parent function. You should be pretty good at this one because that's the square root function. 2 and 9, 3. We have the opportunity to make our next point, which we usually haven't done. It's 16, comma 4. Here's the original square root function, and that's f of x. Okay, now I'm going to change colors here. Let's make it orange and explore this 1/4 square root of x. We've got you set up to put the same points in there for 0, 1, 4, and 9, but now when the output happens, everything is cut into fourths or divided by 4. 0, 0 will still be a point. Square root of 1 is 1, but 1/4 of that is 1/4. When I put a 4 in, I get 2. And 2/4 is 1/2. And when I put a 9 in, I get 3/4. You know, we have enough space to put in the next square rootable number, which is 16. And when you put a 16 in to the square root, that's 4, 4 over 4. We finally get to 1. Let's put those points in and see what it looks like. 0, 0, 1, 1/4, 4, 1/2, 9, 3/4, 16 is finally 1. Oh my goodness, that is a slim looking graph. That is g of x equals 1/4 square root of x. The effect of this is called a vertical compression. All the y coordinates have been squished and squished meaning cut into fourths. So that the square root function, that one in red, it's kind of just been like pushed down so that all the points are just 1/4 of where they used to be, the y coordinates. Okay, vertical compression. Let's switch colors here and go to 4 square root of x. Thankfully, those same numbers working on the inside will work. 0, 0. A 1, I go to 4. When I put in a 4 into the square root, that's 2, that's 8. And then 9, 12. We could go out a little further. Let's try what happens when we put a 16 in. That should be 16, 16. We'll put those points in. You put them in as well. 1, 4, 4, 8. I think that's it. 9, 11, 12, and 16, 16. That's h of x equals 4 times the square root of x. What's happening here? Well, the x coordinates are all the same, but the y coordinates have been pulled up, almost as if all those points have been stretched vertically. That is a vertical stretch. I'm going to erase those arrows because it's going to put some more in there. That's a vertical stretch. All right, 3 down, 2 to go. J of x equals the square root of 2. Now this one, I'm going to share with you a little trick. Any number will work in here, any number, as long as it's not a negative number. But these numbers that we usually put in, 1, 4, and 9, when I put them in there, we're going to be taking then the square root of 2, the square root of 8, and the square root of 18. Those are not nice square rootable numbers. So I'm going to do a little math here, and I'm going to try to examine this inside the I think it's called the argument, the radicand, no, the argument, the 2x, and I'm going to force it to be the nice numbers that I like. 2x, I want it to be equal to 1. This next one, I want it to be equal to 4. And the next one, I'd like it to be equal to 9. I'm going to use that 16. I want 2x to be equal to 16. So when I solve all those, I need x to be equal to 1/2. So I'm going to change this to 1/2. For the 4, I need x to be equal to 2. So I'm going to change that point to 2. I'm going to need x to be equal to 9/2, and that's okay. It'll be a nice y coordinate, which is nice. And then x is going to be equal to 8. See what I'm doing here? I'm forcing what's inside to be something nice and easy. That hard part's done. Now it's the easier part. When I put something into the square root of 2x, I get something nice out. When I put 1/2 into the square root of 2x, that means it's really being the square root of 1. Oh, that becomes 1. When I put a 2 into the square root of 2x, that becomes the square root of 4, and that's 2. You will find 9/2 yields 3, and then when x equals 8, that's my new point, that's going to be the square root of 16, that's 4. It's those points that are going to be real nice to put in. 0, 0, 1/2, 1, 2, 2, 9, 3, 8, 9/2. Sorry, that's 4.5, 3, and 8, 4. If we had the next one, it would be what, 25/2 and 5. 25/2 is 12.5 and 5. So I was able to put another point in there. Is that right? Oh, let's see. 0, 1, 1/2, 1. This point is off. It looks a little weird. No! I'm going to have to just keep it where it is. 1/2, 1 should be right there. That looks more in line. And that is j of x, which is the square root of 2x. What's happened here? Now it's almost as if this red line, the original, has been kind of pushed from the end so that it bows out. That is called a horizontal compression. Now, last one. How about green? The square root of 1/2 x. Same thing happens. You can put in these original points, but I'm going to make it so that 1/2 x is nice. They're nice numbers. X over 2 needs to be equal to 4. X over 2 should be equal to 9. And x over 2 should be equal to 16. That means x is going to have to be equal to 2. So I'm going to change that to 2. X needs to be equal to 8. X needs to be equal to 18. And, x would have to be 32. That's going to be off my scale. That's okay. And again, you don't have to do this, but things are going to be a little easier to find, in my opinion, when you put in nice, easily square rootable numbers, so you don't have to use your calculator. 2, 1. 8 means the square root of 4, that's 2. 18 really means the square root of 9, that's 3. And if we could go out to 32, that would be 4. Let's put those points in. 0, 0, 2, 1, 8, 2, 18, 3. The effect of this one, this green one, which is k of x, equals the square root of 1/2 x, is that is a horizontal stretch. It's kind of hard to think about the horizontal part, but this 1/2 x, think of it as meaning in order to get the same y coordinate, I've got to go twice as far to get to the same square root. Whereas in this one, this square root of 2x, I only have to go half as far as I usually did to get the same square rootable number. Okay, we're almost done here. Let's generalize it and give you an option to kind of practice. A vertical stretch is given by a times f of x, as long as a is positive and it's bigger than 1. If you have a f of x, a on the outside, and that a is a fraction, or officially it's sandwiched between 0 and 1, that's going to be a vertical compression. All right, so now numbers on the outside are vertical changes. If we want a horizontal stretch, we need it to be f of, I'm going to change it to b of x, b times x, where if b is a fraction, that would be a horizontal stretch by 1 over b. So if b is inside there and it's 2, it's going to be a horizontal stretch by half. Okay, and if you want a horizontal compression, that's also f of a multiple inside x, and if that number is larger than 1, that's a horizontal compression. By the factor 1 over